On a high note, this is a student that's under the research mentorship of Dr. Robert Harris.
Yes, I did the method development of the synthesis of amines, and I'm John Bolinger. So, amines, they're nitrogen-containing compounds, as shown in those two drugs on the far right. And why are amines important? They're used in a ton of different various markets, such as surfactants, pesticides, pharmaceuticals, and water treatment. And I'm kind of going to focus on pharmaceuticals today. So there's really three main traditional processes of making amines. This first one is the substitution of alkyl halides. This one is not great. So the Williamson ether synthesis is adding an oxygen group on, you're replacing that bromine, and so you create an ether. This works, it's great, and so you would think that it'd be a pretty similar process for making amine, because nitrogen and oxygen are pretty similar. Sadly, it is not. Even if you use a mole-to-mole ratio, so it's the same ratio, you end up getting all three of those products, so it's very impure. And if you use a bunch of, if you increase the ratio and use more of the alkyl halide, you actually get really just the tertiary amine. It's not great. And then I have Gabriel synthesis. So for Gabriel synthesis, it was created by Sigmund Gabriel in 1887. So it's been around for a long time, and this solved the issue of alkyl bromide. So you start with a phthalimide over here at the far left, come in and add your alkyl bromide, and it adds onto that nitrogen, and you get this new nitrogen with the substitution on it. Then you come in with hydrazine and heat, and it will break off that nitrogen group, leaving you with your primary amine at the far right and that extra product. Issue with this is it takes 3 steps, and you're left with an extra product that is really useless, and you have to do purification to get rid of it. The next traditional method is reductive amination. So this one is the best of these 3 traditional methods. Unfortunately, it takes 3 steps, so again, that's a lot of waste you have because you have to do purification after each step. But it follows the process of an amine adding or reacting with a ketone or aldehyde, which is just the carbon double bonded to an oxygen, and you get an imine, and then you have to create an iminium ion with acid workup, and then lastly, come in with a base and remove that to get your amine. So hydroamination. So those 3 are all the traditional methods. This one is more modern, and so it's atom economical. It saves the overall process. It's less steps, and it reduces the amount of waste that you have, which, you know, people are in the business of making money. They don't want to waste stuff. The problem with this is that it is not perfect yet. So there's intermolecular and intramolecular hydroamination that I'm going to focus on today. Intramolecular hydroamination works great. Roski has done it a number of times. If you just have your carbon bond, the alkene bond over here, and you have your nitrogen bond in the middle, or it's just in the same molecule, and it will react throughout the molecule, pretty easy done. Intermolecular hydroamination, on the other hand, is not as easy to do. The only previous literature that I could find of this successfully working is using this indole over here. And so if only one molecule can be used for this, then that's not great. So our goal is to make this more generalizable and try and make a ligand that can create this or can make these molecules more easily. And so, again, like I saw on the previous page, you have iridium. We are transitioning to using zinc. It's a lot cheaper than all these Nobel metals. It's also less toxic for you. I mean, everyone has zinc in their body. You don't really want gold or other stuff like that in there. It's also redox, and so basically all that means is it has a long life span, so you can keep using it over and over again versus some of these other noble metals. You have to keep replacing them, which increases your cost as well. So this goes into my ligand design. The whole idea behind this concept is to add my 2 different substituents on my nitrogen groups that can then kind of simulate the intramolecular hydroamination. So you'll have I have my alkene bond bonded to my zinc, and then the amine group will come in up there, and it will attach down here to this oxygen. And this is to try and keep it as close as possible to make it seem as similar to intramolecular hydroamination as possible. Unfortunately, though, this did not work. So this was synthesized by Ethan de Blasio, and he went and took it to Clemson, and this is a crystal structure for it. And as you can see, that instead of creating the monoligated product that you saw on the previous page, instead it's a bis complex. And if you look on the far right, those isopropyl groups are right on top of each other. So we came up with this new idea. Our new idea is to add additional methyls onto the groups. You can see this methyl here and the two others on these two. This is to increase the bulkiness of it to try and prevent it from making the bis complex again. It's also to try and just simulate that intramolecular hydrogenation. So this is an NMR machine. Scientists or chemists take NMRs all the time. They allow you to analyze what the product looks like. And they're pretty similar to MRIs. They do about the same thing. And if you look at this chart over here, it's a little confusing, but I went through and labeled them to try and make it as easy as possible. So you can see the protons over there. You have about 9 to 1, or 9, and then 3 over there, and then 6, and so it's a 3 to 1 to 2 ratio. And that resembles the different methyls that you can see in the molecule up there at the top right. So for my future work, we want to attempt to add the ligand that we have created to this dimethyl zinc to then create this catalyst over there at the far right. And once we have done that, we can then use that catalyst to come in and add it to our these two starting materials to make the primaquine that you saw on the first slide. I'd like to give my acknowledgments out to Furman and Clemson for letting us use their department and letting them let us use their equipment. Also for Ethan de Blasio for his previous research, and Wofford College for their undergraduate research fund. Any questions?
John, so you mentioned that this could be used in pharmaceutical production. So like what kinds of drugs would be interested in?
So it would be really any drug that has an amine, which makes up about 84% of the market. And so, like I tried to show with that last one, but it would just allow you to create that drug more easily.
Faster.
Yeah, it'd be a one-step process instead of multiple steps.
Yeah.
Dr. Harrington?
John, I think it's super clever to have the NH come and hydrogen bond to the oxygen on the sulfur. Have you seen any evidence of that happening?
Not necessarily. We just assume that's what is happening, but like next year the goal is to try and simulate it or run computational chemistry to try and figure out if that's actually what happens, or if like it bonds somewhere else.
Yeah. It seems like there may be some spectroscopy that would let you know if that were in fact happening, but it's a great idea.
Yeah, we also haven't gotten quite that far yet because we haven't created like a monoligated. Yep. Any other questions? Thank you.
All right. Thanks, Mike. All right, this concludes our